Hello everyone, welcome to topic 8.9, Henderson-Hasselbalch equation. By the end of this, you should be able to identify the pH of a buffer solution based on the identity and concentrations of the conjugate acid-base pair used to create the buffer. Let's revisit the buffer that we formed in section 8.8. The buffer contained 2 moles of acetic acid and 2 moles of sodium acetate dissolved into 1 liter of water. This was a buffered solution since both the weak acid and its conjugate base are present. So we need to remember that a buffer contains a weak acid and the conjugate base of the weak acid. We can look up the pKa for acetic acid, which is 4.76, and use it to calculate the pH of the buffer system using the Henderson-Hasselbalch equation. So the original concentrations for the conjugate base and the acid are 2 moles divided by 1 liter because they both have the same amount of moles and are both dissolved in 1 liter of water. And so they are going to have the same equation, which means that this is 1 and the log of 1 is 0, so that the pH is equal to the pKa in this case. The pH and the pKa are the same because the concentrations of the conjugate acid-base pair are equal. The log of 1 is 0, so the term drops out. The pH of a buffer system is dependent upon the pKa for the buffer and the ratio of the concentrations of the conjugate acid-base pairs. If 0.1 moles of sodium hydroxide were added, it will react with the acetic acid to form the conjugate base as shown below. The sodium hydroxide is a strong base, so it is the limiting reagent. So we can assume that the reaction will consume all of it. So a very little amount is added, and that is actually here. So that's the initial concentration. It's going to react with some of the acid in the buffer system. And so because it should go to completion, we should use all of this, and this is 0. And we complete the rest of the ice table as shown. We see that the addition of a small quantity of a base has little effect on the ratio of the conjugate base to its acid. And so if we recalculate this, we see that the pH actually doesn't change very much because the ratio is still almost 1. And so the pH is still very close to, if not equal to, the pKa. The same idea applies to adding an acid to a buffered system. If 0.01 moles of hydrochloric acid is added, it reacts with the acetate ions of the conjugate base to form acetic acid as shown below. Hydrochloric acid is a strong acid and is the limiting reagent, so we can assume that the reaction consumes all of it because it's added in a very small amount. It is all consumed, and so we complete the ice table from there, where this is our initial amount for the hydrochloric acid or hydronium ion. We see that the addition of a small quantity of an acid to the buffer system has very little effect on the ratio of the conjugate base to the acid. And so this is still roughly equal to 1. So this whole term drops out. And so pH is still approximately equal to the pKa. So it does not change very much, if at all. Okay. For our example problem, we are going to calculate the pH of a buffer solution for a weak acid, HA, if the concentration of HA is 0.137 molar and the concentration of its conjugate base is 0.972 molar. The Ka for this acid is 1.51 times 10 to the negative 5. So the Henderson-Hasselbalch equation is pH is equal to the pKa plus the log of the conjugate base to its acid concentration. Okay, substituting for the values we know, pH is going to be equal to pKa, means we're going to take the negative log of this. Remember that pKa is the negative log of the Ka value. So we're going to take negative log of the Ka value, which is 1.51 times 10 to the negative 5th, plus the log of the conjugate base concentration divided by the acid concentration. Plugging these into our calculator, we should get that this whole thing is equal to 672, which is our pH of this buffer system. Okay. And this is using a calculator. We take the negative log and then add it to the other log. Okay. Now, for our redo, calculate the Ka based on the following information for the following unknown acid HA. Sorry, there was a lot of followings in there. The pH of a buffer system is 219. The buffer is composed of 2.43 moles of HA and 1.75 moles of Na dissolved into 1.92 liters of solution. So our first step is to determine the concentrations of our acid and the conjugate base. The conjugate base is going to also be equal to the concentration of the salt dissolved in there, because these two will fully dissociate. Okay, so we're going to, concentration is moles over liter, so we're going to take the moles of acid we know we dissolved, so 2.43 moles, and we're going to divide it by the total volume, which was 1.92 liters. Plugging that into a calculator, you should get 1.27 molar for the concentration of the acid. We will repeat this for the concentration of the conjugate base. So we take the total number of moles, which is 1.75 moles, of the sodium salt for the conjugate base, which is equal to the conjugate base concentration, divided by the total volume. And you should get 0.911 molar. Okay. Using the Henderson Hasselbalch equation, we know that pH is equal to pKa minus the log, not minus, plus the log of the conjugate base concentration divided by the acid concentration. However, we know pH, we want to find Ka, so we're going to look for pKa from this. So rearranging, we see that pKa is equal to the pH minus the log of the conjugate base divided by the acid. Plugging in what we know, the pH was 4.219 minus log. No. This is kind of in the way, but we'll make it work, I guess. And this is 0.911 divided by 1.27. So when we plug this in, we should get that the pKa is equal to 4.333. Using our log knowledge, we know that the Ka has to be equal to 10 to the negative pKa, or 4.333. Plugging this into a calculator so that our exponent is a whole number, we have 4.65 times 10 to the negative 5 for our Ka value. And so this is the Ka of the HA acid that we were given for our unknown acid. Okay, so using the Henderson-Hasselbalch equation and what we know on how we can calculate concentration, you are going to complete the UDOs. Please make sure you check your work, and thank you for tuning in.